o'clock yet, but it will be in a few seconds. Oh, and there it is. Okay, so we're down to 7. Well, okay, 12 if you count the 5 people online, but private number and zeros. Still a little time left. Okay, so today's topic is the last topic that will be featured on the final. So this is part of homework 12. Homework 13 is on conic sections, which is Monday's topic. There will only be the homework on that, not appearing in the final. Next Wednesday, class will be a review session. We'll talk about the practice final and any final related questions have. And then, so 12 days from now is final. Okay, welcome. All right. Okay. So, all right. Following up on last time with polar coordinates. I previously covered arc length and areas when it comes to these parametric curves. Now I'm going to specialize all that polar coordinates. So the first thing I'm going to deal with area. So the contrast. You have a region like this. The two x values, y-axis, then the top boundary is some curve. Derived by a Cartesian equation, y equals f of x, then you know how to get the area of the shaded region. That's the definite integral. Okay. Now, by contrast, what I'm going to show you today is suppose we have a region defined by a polar curve, polar equation. R is equal to f of theta, and you want the area of a region bounded by f of theta, and then two particular theta values, arrays corresponding to two theta values. So we have theta equals A and theta equals B. So how do we get the area of this shaded region? Okay. Using a similar approach. Okay. Now, what's going to help us is a formula for the area of a sector of a circle. Okay, so I have a circle of radius r, and I want the area not of a whole circle, but just a sector of it, basically a pie slice, where the angle swept out by this, like if we sweep the area from this ray to this ray, the angle that's covered in between is theta radians. Okay, then what is the area of that? Does anyone know offhand? I don't know what class you see this in, maybe in a trig class or something. What is the area of this pi slice? Using R and theta. But maybe able to extrapolate from formula for the area of a whole circle, pi r squared.
I'm just guessing.
Well, it sounds like we're trying to take for a fraction, like if we take a whole circle, pi r squared, but if we keep in mind that theta equals 2 pi covers the whole circle. So if I take the portion that we have, theta, and then divide by what we get for a whole circle, then we simplify that and we get 1/2 r squared theta. So if I were to take this region here that I want the area of, and I divide it into infinitely many, infinitely thin sectors, where the angle corresponding to each one is d theta or delta theta. And then the radius for each one would be the value of f at the appropriate theta value for each one of these sectors. So the area bounded by theta equals a, theta equals b, r equals f of theta is approximately a sum. If I break it down into n sectors, I could use this formula for each one. So 1/2 f evaluated at some angle theta I, the whole thing squared, times delta theta, and also a uniform delta theta thickness for each sector. So then I could add all of these up. And what kind of sum is this? What do we call this? Kind of sum, where we're but that for terms of this kind of product of a function value and then a spacing. It is a Riemann sum. So the exact area is going to be the integral of 1/2 f of theta squared d theta. So this is a formula used for area defined by a polar curve. For this kind of region between theta equals a, theta equals b, and r equals f of theta.
I'd say it is on the other side of the.
Yes, it's approximately equal to this, but it's exactly equal to this.
Last thing of the revision
This one?
above that.
Oh, delta theta. Oh, well, okay. I have to write delta theta over here. And then in the limit, that becomes the differential d theta. Okay. Okay. An example of how this formula is used. Suppose our polar curve is just r equals theta. And then we have a equals 0, b is equal to 3 pi over 2. So since r of theta is equal to theta, that means that as we trace the curve out, at first we start at the origin, and then as theta increases, the distance from the origin increases. So we get something like this. So it's the area of this region right that I'm shading here. Because remember the angle 3 pi over 2 is down here. So the area of this rather odd shape is 1/2 the integral from 0 to 3 pi over 2 of your r squared, so theta squared d theta.
Is it
What?
Uh,
A is 0. Yeah. Make that more 0 like. Okay. So then just go ahead and integrate this normally. 50 over 3, limit 0 and 3 pi over 2. And once you do all the algebra, you get 9 pi cubed over 16. Any questions on this first one? Another? All right, so here we have a region that's bounded by theta equals 0, theta equals pi over 4, and r is equal to square root of sine theta cosine theta. So the curve, what it looks like is, so we only care about what's going on between these rays, theta, the positive x-axis, which is theta equals 0, and then this line, theta equals pi over 4. So it's going to be contained within here. So as theta sweeps from 0 to pi over 4, we start out at the origin at r equals 0. And then as theta increases, distance from the origin increases until once we get to theta equals pi over 4, then under the square root sign, you're going to have 1/2. So that so out here, this distance is going to be the square root of 1/2 or square root of 2 over 2. So it's this region that we want the area of. So this is the polar curve. Defined by our polar equation. So the area be 1/2 integral 0 to pi over 4 of r squared. But this is a toy problem, so if it works out nicely, you know, so you square r, but that just cancels the square root. Um. Okay, can any of you tell me two different approaches to this integral?
Substitution.
Okay,
Double integral, well, double angle
yeah,
identity.
double angle formula, because this right here is equal to sine two theta over two. You can integrate that, or you can, yeah, do a u substitution. If you let u equal to sine theta, then du is cosine theta d theta. Not that I care which approach to use, but it's good to be aware of as many integration strategies as possible. But for the record, the answer turns out to be 1/8. Okay, in the notes, I ended up using the double angle formula approach. Okay. For purposes of test problem, and I think I probably only had at most one problem of this type on the final with the computing area. There's two parts to it. One is, do you set up the integral correctly? Because so far in these examples, that hasn't really been a big deal. But for other problems that I'm about to do, it can be a little more involved. So do you have a correct integral set up? So there'd be some credit for that. And then do you evaluate it correctly for the rest? So of course, each problem's only worth 5 points, so I'm not talking a lot of points to line anyway.
Purposely final?
Sorry,
Is it like 100-point final? So
yeah, so 20 problems, 5 points each. Now, it sounds like a lot of problems, but some are quick. You have 2.5 hours. And I reserve a right to curve if needed. It turned out not to be necessary for a midterm, but I won't rule it out for a final. I think you're all doing the academic equivalent of point shaving, then that's not gonna end well for you, so. Like, I'll just do half problems, he'll curve us, but. Okay. I guess given the kind of topics I've been covering lately, logging curve is giving a whole new meaning. Okay. So here we have for the next example, a region defined a little differently. So we still have a polar curve. R is equal to 4 plus 3 sine theta. So the area by this curve and x equals 0. So in other words, the y-axis. Now, what we're looking at? Oh, I don't have this one plotted. So one of our boundaries is a y-axis. X equals 0. So the polar curve, so for instance, when theta is equal to 0, when theta is equal to 0, R is out here. So this is a point that's on our curve. But keep in mind, the y-axis, what angles does it correspond to? Yes, and? Yeah, 3 pi over 2, or by periodicity, minus pi over 2. So here we have theta, pi over 2, theta equal to minus pi over 2. So for example, as far as how a polar curve behaves, let's say when theta is equal to pi over 2, then we're going to be up here at 0, 7. So R is going to be steadily increasing. So it's 4 here, 7 here. Whereas at theta equal to minus pi over 2, sine theta is equal to minus 1. So this point, 0, 1, is also in the curve. It's probably not really the shape, but it does pass through these 3 points. Okay, so we want the area of this region. All right, so, now because if you look here, sine theta, as you know, ranges between -1 and 1. So that means that R has to be between 1 and 7, because it's 4 minus 3 or 4 plus 3. So you know you're going to get R values between 1 and 7, and that's what actually happens for these angles. So the area of this region is an integral of 1/2 times your R squared. Okay. And with limits from minus pi over 2 to pi over 2. Any questions on the integral setup? Now, in previous examples, I defined the region boundaries using theta equals something, which is the most straightforward case. But if your region is described with different boundaries, like in a Cartesian equation of a line, like x equals 0, y equals 0, then the question asked in that case is, what angles does that line correspond to? And that's where you get plus or minus pi over 2. Whereas if we're looking at the if we had a boundary as the x-axis, so y equals 0, what angles will we be looking at in that case?
0 and pi.
Yes, 0 and pi.
We'll never have a more complicated equation like x equals a polynomial or something.
Oh, no, yeah,
Okay.
yeah. I mean, maybe that could be done, but I'm not gonna make you do it. All right. Now, if you really don't like to deal with negative theta values, another way to have done this would have been if you go from 0 to pi over 2 to cover the top portion, then you could do 3 pi over 2 to 2 pi for the other portion. That would give you the same area by the periodicity of sine. Okay, now, if you go ahead and boil this. Okay, and you get 16 plus 24 sine theta plus 9 sine squared theta d theta. Okay. Now, how do you handle that? Sine squared theta. Can't integrate that directly.
Cosine of the theta, the double angle.
Not double angle, but half angle. Yeah. Yeah, this is 1 minus cosine 2 theta all over 2.
Yeah.
So anytime you have a sine squared or cosine squared, it'd be 1 plus. Then you can do that. Okay. Does anyone tell me why I can ignore that term?
It'll be a constant.
Well, not a constant, but well, technically it would be constant, but there's more to it than that. You get 0, why is, well, how do you know you get 0?
Sine both the endpoints give you 0.
That is what happens, but a more concise reason, it's an odd function. And we're on a symmetric interval. So from minus pi over 2 to pi over 2, the integral of an odd function over such an interval, like minus a to a, is 0. So the integral of that term is gonna be zero, so you can just ignore that. Whereas the other terms, the 16 and the sine squared theta, those are even functions. Now, those are not gonna be zero. But because these terms are even functions, how can I change the integral? Take that into account.
From 0 to positive 2.
Yes, but what else do I have to do though?
Fine.
Yes, so I could, yeah, so if I get rid of this 1/2 and go from 0 to pi over 2. Now, as far as the anti-differentiation work involved, that doesn't help you at all. But if I change this to an integral from 0 to pi over 2, they would tell me why that may be preferable.
Less terms, because it'll.
Yeah.
Great.
Yeah, because certain terms you can say, oh, it's gonna be 0. Also, I think it leaves you, it's less mistake prone. Because you're plugging in pi over 2 minus pi over 2, you're basically asking to make a sign mistake. So by changing a limit to one of them being 0, you can help yourself there. So that's something to consider taking advantage of when it comes up. Okay, and so this works out to be 41 pi over 4, details in notes. Well, after this, it's not very interesting after this point. Now, any questions about this one? The next example, or the next few examples, a few more examples here. Okay. The setup of the integral is a little more involved than before. Find the area of a region that's inside one loop of this curve. R is equal to sine of 2 theta. So in this case, I've not told you what the theta limits are going to be. They have to be figured out based on the fact that it's one loop. So the way the curve looks is we start at theta equals 0. Get something like this. So what do you do to define one loop? Because at some point, as I start here, I come back here, and if I let theta keep going, I'd have more figures like this. But we just want one loop. So you check, when is R equal to 0? So certainly when theta is equal to 0, you'll start out at the origin. So the question now is, when is the very next angle where R is going to be 0, meaning you've come back to the origin? Yes, because so it's because plain old sine is equal to 0 and 0, and then again at pi, but we have sine 2 theta here. So we want, so those are our theta boundaries. So from as theta goes from 0 to pi over 2, go out here and comes back home. All right, so that means that the area is 1/2 equal from 0 to pi over 2 of sine of 2 theta squared d theta. So. So if I want to rewrite this in a way that can actually be integrated, what would I end up with? What has to be done inside? Yes, yes, which, and in this case, what would it give me? Yes, but well, give me the whole fraction. Yeah, 4 theta, because we had 2 theta to start with. Okay. And, you end up with, pi over 8, actually, the only contribution to the integral ends up coming from the 1/2 that we have here. The integral of a cosine part, in this case, turns out to be 0. Any questions on the setup, especially of this one? Right. Okay, 2 more examples of area stuff. And a little bit about arc length. Okay. I want the area of the region inside this curve, r equals 3 cosine theta. And outside curve r is equal to 1 plus cosine theta. All right, so we're looking at the area between 2 polar curves. Now I've not given any theta boundaries, so once again, you have to figure out what those will be. So the question to ask is, where do these 2 curves intersect? So you set them equal to each other and find the theta values are equal. So you solve this equation, 3 cosine theta equal to 1 plus cosine theta for theta. What you can do is, ultimately you want to solve for theta, but as an intermediate step, you can solve it for cosine theta. So if you rearrange this equation, what do you get for what cosine theta must be equal to?
Oh, 1%.
Yeah, 1/2. Also known as, yeah. Okay. Then the question is, at what angles is cosine equal to 1/2? Where else? You want cosine is an x value. Also, cosine is an even function. But 5/3, also known as minus pi/3. That's why I mentioned even function. If cosine theta is 1/2, cosine of minus theta is also 1/2. Okay, so those are our limits. Okay, so So at those theta values, both r's are equal to 3/2. So we have 3 cosine theta. That's gonna be the r equals 3 cosine theta, that's gonna be a circle. Of radius 3/2. So it starts out here when theta equals 0, when theta is pi/2, it lines up at the origin. So anytime you have r is a constant times cosine theta, it's a circle of radius half a constant, and center is located at x equals half that constant. The other one, r is equal to 1 plus cosine theta. So when theta is equal to 0, starts out here at 2. And when theta is equal to pi/2, it's going to be 1. And when, okay, also equal to 1. All right, so so this is the other curve. R is equal to 1 plus cosine. Okay. I mentioned it's a region that's inside the first curve, which is a circle outside this curve right here. So it's the area of this region. And apparently I've drawn this just well enough so that the intersections really do appear to be roughly plus or minus pi/3. Okay. So the area, okay, maybe a little off, but 1/2 integral of the minus pi/3 to pi/3. But what do I have for the integrand? Be careful, the area between two polar regions.
So that
Polar
would
curves.
be,
Well, not exactly right minus left. Keep in mind the formula for area of the
have
polar
to
curve.
square-
And it's the thing about it, we have to be careful about how we square.
like, each one separately.
Each one separately, because, yeah, so it would be 3 cosine theta, the whole thing squared, minus 1 plus cosine theta, the whole thing squared. So this part would cover, most of the circle except for what's between these two rays. And then, we're subtracting out this portion. So we're subtracting 2 polar areas. Okay. And it's pretty much the same kind of trigonometric manipulations that we've seen, so it's not very interesting. But you can then get details of the notes and see what the answer turns out to be pi in this case. Any questions on that one? Last example involving the area. So I do not have as many examples about length. So, long case. The area inside. Curves r is equal to sine theta. R is equal to cosine theta. Now, what I mean by that is, if I were to draw these two, So for R equals cosine theta is a circle with its center on the x-axis. If it's R equal cosine. And then we have R equals sine is a circle of the same radius, but it sits on top of the x-axis. Okay. So the area that's inside both curves, that's actually not that word. So it's this region in between. So that's a little trickier as far as from an integral setup point of view. So really what you're going to do is you're going to look at where they intersect. This intersection point happens at what angle? Where sine and cosine equal to one another? Yes. So at that ray, what that means is to get the area of the whole shaded region from 0 to pi/4, we're going to use sine. And then for the remaining portion, from pi/4, pi/2, we use cosine. So we're taking two polar regions and slapping them together, defined by different polar curves. So what you'd have to do for both of these integrals is use the appropriate half angle formula. The 1 minus cosine theta over 2 for the first one, 1 plus cosine 2 theta all over 2 for the second one. And you end up with, in case you want to try this at home, it's trait expression pi minus 2 all over 8. Kind of weird, but. Okay, so any questions about these area ones? Try to make sure whatever's on the test is not too nasty. Give a hint as needed.
It's the trig identities that I just.
Yeah, well, we've been given the formulas.
Yeah.
I don't recall if I put that on the practice. Okay. Oh, okay, but right on the practice, I don't have them, but now whatever needed is another matter. Okay, or I could also write them on the board. Oh, wait a minute. It looks like I just wasted everyone's time because there is not a problem about area, polar area on the final. I think it's one of those speak for yourself situations, but okay. Okay. Yeah. So, okay, but there may be other problems where quick identities are needed, so I'll keep that in mind.
Make sure you email it.
Oh, right, okay. In that case, then I'll just do it. I'll just add to the sheet in the PDF. Okay. Alright. Now, from the last topic of today. Our arc length. Um. Now, when we look at the control formula for the arc length of a parametric curve, where x and y are both functions of t, the arc length formula is the integral from a to b of square root of the x dt squared plus the y dt squared dt. Now for a polar curve, get the arc length of that, we could just use this because if you have r is equal to some function f of theta, then we can directly write this directly as a parametric curve. X is f of theta cosine theta, y is equal to f of theta sine theta, and I could take the derivatives of these with respect to theta and just plug them in here, and I'm done. But if I actually put this general form in there and work all this out, it simplifies a little bit. So, and if we assume that theta is between A and B, then the arc length turns out to be integral from A to B of square root of r squared plus BR d theta, the whole thing squared. So these two formulas are equivalent. Just that this one is for a specific case of x and y defined by this r equals f of theta. So the way to think about it is f of theta, the whole thing squared, plus f prime of theta squared. So you can just jump directly to that. So then there's only one derivative to figure out. There's two. Oh. Oh, I only have one example here. Yeah, it's not a very interesting topic.
On the thing,
What?
if there's arc length is on the museum.
It is.
Yeah.
So there's a. So it's maybe only one, but it's a very worthwhile one. Okay. Okay, so what I have for real test made up. I will take it and see what trig identities I needed to do it. And make sure those are available. Because the only trig identity I can count on students knowing is sine squared plus cosine squared equals 1. Well, as Dr. Lee said, there are really only 3 trig identities you need to know, because all the rest you can figure out from them. So if you know that one and sine of sum or difference of angles and cosine of sum or difference of angles, so many other formulas come from that one. I guess sine squared plus cosine squared equals 1 comes from 1 as well as 2, so we really only need 2. Okay, so if my polar curve is r is equal to cosine theta between 0 and pi over 2. Okay. So because we're going from 0 to pi over 2, it's a semicircle of radius 1/2. So we're starting out here at beta equals 0, and then as we go, okay, it goes from 0 to pi over 2, we wind up back here at the origin. So it's this length we're going to get. Now. um, So d theta is minus sine theta. So the arc length. The integral from 0 to pi over 2, square root of r squared. Plus. Dr d theta squared. And that works out rather nicely. So we just end up with. The integral of 1 d theta. Yeah, it's not very interesting. Pi over 2. Now. You might be, we could also, what was the other way we could have gotten the arc length without doing an integral in this case? What? Circumference, yeah. Yeah, because the circumference of a whole circle is 2 pi r. It's so pi r for a semicircle, the radius is 1/2. So we can get pi over 2 that way, but. But if you don't, if it's not that simple a case, then you're doing an integral. Okay. That's my phone blowing up. All right, so any questions about polar area or length? Oh, wow, we're getting done early. Did anyone look at the practice final yet?
Hmm.
Okay, well, yeah, it's a little early, so. Okay. Are any homework questions? Yes. Okay,
On the homework questions, when we have to determine like. When we're finding the area between curves and it's not an ellipse, and we have to find like the boundaries.
oh, okay,
I don't ever get the right boundary,
oh. Okay,
or I just do, I don't know. It's for like questions 12 and 13. I know how to set it up, I just don't know how to get the boundaries.
Okay, which one is it, number?
The 12 and 13.
Oh, both, okay.
Yeah.
Oh, it's parametric curves, okay.
Yeah.
Okay, above the x equals. I'll go this parametric curve and T to 1. Okay, so. All right, this is homework number
11.
12.
okay, so number 12. Okay, can you read off the parametric curve?
X equals e to the negative t. And y equals t squared plus 2t plus 5.
That's a weird one, okay. All right, and so it's region above the x-axis,
Above the x-axis
And-
between 0 and 1.
okay, and the t going from 0 to 1,
Yes.
okay. All right, so. Okay, so if we see where we're at when we plug in t equals 0 and 1, so t equals 0. We have. X is 1. And then y is 5. Okay, and then when t is equal to 1, we have x is e to the minus 1, which is roughly like 0.36. And y is equal to 8. Okay, so. So e to the minus 1 is somewhere in here. Okay, so we're starting at this point, 1 equals 5, and we wind up here. Okay. Something like that. Can't grab it in my head. All right, so, okay, so one issue of this is because the curve is going this way. Okay, well, the thing is, if you got the limits in the wrong order, you get a negative value and you just negate it. So I don't know if that's what happened in your case.
Mhm.
Because the area is gonna be integral from 0 to 1 in T. And you have, your Y times dx dt, but minus because the curve is traced out from right to left. So the minus are just gonna cancel out. Okay. So is that what, is this the integral you set up?
Maybe I used the wrong formula, because I thought I had the x and y squared.
Oh, okay, so for area, it's the integral of y dx, but that's the integral of y of t x prime of t dt for area. Yeah, okay. Was that you too, or?
Probably.
Okay, alright. Morgan, do you have a,
This is a silly question,
okay,
I think. Okay. I just wanna show it to you.
okay.
I was asking them about how to fill it.
Oh, but, or to, after class, when everybody's after,
Yeah.
okay.
Sally, did you have a number one? Or, okay. Anyone else? Yes.
Is that minus e to the negative t, or is it?
Yeah, it is minus e to a minus 2 because I take the derivative.
And knowing that the curve is like going this way rather than
Yeah.
down is just,
Well, you can see that from plugging in these extreme t values and you see like, oh, I went from higher to lower.
okay.
Yeah.
It's there, it's something.
So if you get a negative answer, just negate it.
Yeah. Any other questions? Okay. We'll see who shows up on Monday.
I feel like that's the, wait, is Monday the review?
Monday is conic sections.
And that one's,
That's
Not in the final.
Yeah.
Be like the last homework.
Yeah, but
it's not on the final. So we.
yeah. Yeah. Okay.